Hi, I want to take a look at the error bound for the linear approximation and show you where the formula comes from. So I'll get myself out of the way and we'll be able to see what we're doing here. So here's the setup. I've got a function, y equals f of x, and we're going to use a linear approximation for that function at x equals b. So the linear approximation is L of x, so the linear approximation of x is the function value at b plus the derivative at b times x minus b. So the function is the black curve, the linear approximation, in this case I have it done at x equals 4, is the tangent line. So when we say the error, that is if I plug in something other than 4, the linear approximation is probably not going to give me the same value as the actual function. So I want to know how far am I off? What's the difference? If I plug in an x, the function value is up here, the linear approximation is down here. What's the difference in that? So I'm trying to find out what's the difference between f of x and L of x. Right? And I'm going to find that, as it turns out, by doing an integral in two different ways. So here's this integral of f prime of t dt integrated from b to x. So I'm going to integrate the derivative of this function between my nice value that I'm basing my linear approximation at and this x value where I'm trying to evaluate. I'm going to do this two different ways. Well, the first way is the fundamental theorem of calculus, that to do a derivative, to do an integral like this, a definite integral, you find an antiderivative of this function, plug in the two endpoints and subtract. Well, the antiderivative of the derivative of f is f. So I have f of t evaluated at x and evaluated at b, and I'm subtracting. That's the fundamental theorem of calculus. At least one of the two parts. I never know if it's part 1 or part 2 because I've seen different textbooks call it different things. So anyway, it's one of the two parts of the fundamental theorem of calculus. Anyway, now I'm going to do that same integral again, but this time I'm going to do it by parts. And this is one thing I like about integration by parts, is that any integral you have, if you don't know how to do it, you have the option of taking the derivative of the function rather than integrating the function. Right? So integration by parts, I start off with the integral of u times dv. So I'm calling u f prime of t, and dv is whatever's left, dt. So now taking the derivative of u to get du, that would be now the second derivative of f times dt, and integrating dv to get v, and dt integrates to t plus a constant. Now usually we don't put a plus a constant in here, we just leave it as 0 because it just gets in the way. It doesn't matter. In fact, it cancels out. If you try it with an integration by parts, throw in some other plus c, it cancels out in the long run. But in this case, it doesn't. We leave it long enough that it actually helps us. And someone was really clever at one point and realized that, hey, if I throw a minus x in here right now, it works. Minus x is a constant because in this problem, t is the variable. X is just being used as that upper endpoint. Okay? So x is a constant, so I'm just doing t plus a constant for my integration there. So now, integration by parts. I started off with the integral of u dv, so I have u times v. This is the u, this is the v, so u and v. It's a definite integral, so I need to evaluate between the two endpoints. And then minus the integral of v du. Well, v is the t minus x, and the du is the second derivative evaluated at t. So, doing the work now, I've got the x plugged in for t here, and the b plugged in for t there, and I'm subtracting. This turns into a 0. And I haven't done anything over there yet. So yeah, this turns into a 0. On this one, this minus sign, I'm distributing it into that factor. So instead of a b minus x, it turns into an x minus b. And likewise, this minus sign, I'm going to distribute, well, first of all, pull it inside the integral, and then distribute it into that factor right there. So this becomes a plus on the outside, and the t minus x turns into an x minus t. Okay. So what I have is that integral is equal to this, which is also equal to, where is it up above, this integral here. So I have that, here's the first way I did the integral, and here's the second way I did the integral. What's nice about this is I can apply a little bit of algebra to it and subtract this term over to the other side. Once I get it over there, I'm going to factor out a minus sign from that one and this one. So there's a minus, and this stuff is in parentheses. But this, in parentheses now, is the linear approximation. Right? So what I have on the left-hand side of this equation is the function value minus the linear approximation. And that's equal to this integral that I got from integrating by parts. Right? This shows me that the error, the difference between the function and linear approximation, is somehow related to the second derivative of the function. Okay. Now, let's get the formula out of this thing. So I have the error, and I'm not worrying whether the error is positive or negative. It's just that the linear approximation is different from the function. How much is it? If it's bigger or if it's smaller, this might be a positive number or a negative number. I don't care. I'm throwing an absolute value around it just to make it positive. Okay. So this is equal to the absolute value of the integral because those two things were equal to each other up there. Right? So I just took the absolute value of both sides. Now I'm going to slip that absolute value inside the integral, which actually makes the result bigger. This might be negative, and so I'd be adding up some negatives, where this forces the whole function to be positive, and so you're adding up more positive stuff, and you're going to get a bigger result. Okay. Then I'm splitting the absolute value of a product into the product of the absolute values on this step right here. So that doesn't change anything. That's equal to. Then I've got to get a handle on this integral. So I'm going to do it in two different ways. I'm going to slide down here to see everything. First of all, I'm going to look at that second derivative and say, I don't know what to do with it. I don't know what the function is to start with. But if I could just get an estimate of how big might this possibly be. So I'm going to let m be any upper bound on the absolute value of the second derivative. So I'm going to replace this part of this integral with just a constant m. It's going to behoove me later to do as small a value of m as possible, but m has to be bigger than the second derivative on that integral from b to x. It's essentially telling you how much does the function bend, right? The second derivative tells you about the concavity, the bend in the function. And so the linear approximation is not going to be right if that function is bending. And the more it bends, the further off you'd expect the linear approximation to be. So getting an upper bound on the second derivative is getting a handle on how much is that function bending. So how much is the linear approximation off? Okay. Anyway, there's an m right there. That's constant, so it just comes out of the integral. And then I have the integral of this linear function x minus t. Remember, t is the variable here. So x minus t, there's a u substitution with u equal x minus t. du is minus dt. Anyway, it integrates to minus u squared over 2, and we get that. Evaluate then by plugging the x in for t and the b in for t and subtracting. It's all right here. That's a 0, and the minus minus becomes a plus, and you get this formula. The geometry of what happened here is this: the m is just a constant, so you're looking at the absolute value of x minus t. So in this little picture right here, x is actually, this is the t-axis running horizontally. X is that point there, and b is either over here if x is bigger than b, or b is over here if x is less than b. But either way, that interval from x to b, from b to x, is finding the area of a little triangle, either this little triangle over there or this little triangle over here. But it's a 45-45 right triangle. The base and the height are the same. They're both x minus b. So that's what I'm seeing here, is that x minus b is the base. It's also the height. And then times a half. 1/2 the base times the height is the area of either that little triangle on that side or this little triangle on this side. And that, of course, is then multiplied by m out in front. So the error in estimating a function by a linear function, by the tangent line, is given by an upper bound on the second derivative times x minus b squared over 2. There you go. There it is.